Amanda, and me, Zoe, and Sumner will be talking about Chapter 10.1, Estimating with Confidence. So what does estimating with confidence mean? Well, we want to infer some conclusion about a wider population from the sample data of that population. In order to do this, we will use what is called statistical inference, which provides methods for drawing conclusions about a population based off of your sample data. One inference technique we can use is called a confidence interval, which is what we will be talking about today. For example, say that we want to estimate the mean SAT writing score for all high school seniors in Texas. You'll give a test up to a simple random sample of 500 Texas high school seniors. The mean of your sample is 462 as the score. So what can you conclude about the mean score mu in the population of all seniors in Texas? We can first guess that mu will be somewhere near 462 because the law of large numbers tells us that the sample mean x bar from a large simple random sample will be close to the unknown population of mean mu. Let's say that we are given the standard deviation of SAT writing scores for all Texas seniors. So sigma equals 100. Now typically we will not be given the standard deviation of the population because that is really hard to determine. So when we don't have this information, later chapters will explain what to do when you don't know the standard deviation of the population. But here we do. So let's say sigma is 100. So the standard deviation of your x bar is going to be sigma over the square root of n. So we would have 100 over the square root of 500, because that's how many were in our sample, and that equals 4.5. Okay, remember the 68, 95, 99.7 rule? This says that in 95% of the sample, the mean score of x bar for the sample will be within 2 standard deviation away from your sample mean. In this case, 2 standard deviations away is within 9 points of the observed x bar value. Therefore, we are 95% confident that the true mean of the population will lie within 453 and 471 on your SAT writing score. But the 95% confidence level means that in repeated sampling, the method we use will contain the true population mean in 95% of all samples or confidence intervals.
Okay, so the margin of error is a statistic expressing the amount of random sampling error in a survey's results. A small margin of error says that we have pinned down the parameter of the population quite precisely. And the more confident we are, the smaller the margin of error is. Okay, this is our formula for margin of error. It's z star times sigma over the square root of n is less than or equal to m. And the 3 variables on the left you'll obtain from the problem, and your z star is dependent on what level of confidence you have. And then you will compute your margin of error. If your z star is bigger, therefore your level of confidence is bigger, your margin of error gets smaller. And if your sample size increases, your margin of error decreases. If your population's standard deviation decreases, your margin of error will get smaller. Okay, so say our problem wants us to obtain a desired margin of error. This means that we'll have 3 of the 4 variables, and we're trying to look for what sample size will give us our desired margin of error. So we'll basically have to solve for n. There are multiple ways to do this, and typically we would use real numbers when looking for a desired margin of error. But for this purpose, we'll just use variables and kind of put you through the motions and see how we would solve for n. First, we'll divide by the z star on both sides. And then we can cross multiply these, so we'll have so we'll multiply our sigma times our z star, so that'll be sigma times z star is less than or equal to, and then we'll have our desired margin of error times our,
It's cake.
times our the square root of n. So we'll have m times the square root of n. Okay, and now we will divide by m because That's what we need to get n by itself. So now we'll have the square root of n is less than or equal to our sigma times our z star over our desired margin of error, and this is square rooted, so we need to square it on both sides. And so that's basically what we'll get. Okay, so whatever your n turns out to be, you always want to round up. If you round down, that will give you a margin of error that is greater.
So the first step in an ICCI is to identify the population of interest and the parameter. The second step in an ICCI is to choose the appropriate inference procedure conditions. These will change depending on whether or not you know the standard deviation. Randomness is always the same. It'll either be given or you have to assume it. If you're not given it, you're going to need to say proceed with caution. Independence changes with your standard deviation. And normality, you always follow the 2 rules of thumb that are given to you in class. So you calculate your ICCI or your confidence interval. You're going to do statistic plus or minus z star multiplied by standard deviation over your sample size. And your final I in an ICCI is to interpret your results in context.
As Sumner said, these are all the steps for carrying out an ICCI for a confidence interval. So using the example we used earlier in the video with the SAT writing score, I'm going to just go through the steps of what would go under each different letter. So identifying the population of interest. In this case, it would be all high school seniors in Texas. And the parameter that we're studying is the mean mu SAT writing score for all seniors in Texas. So we would just write that out, what we're looking for and who's our population that we're studying. Next, we would choose the appropriate inference procedure. In this case, we're just going to use a z confidence interval. And we're given that it's random, so this condition is checked because it told us it was from a simple random sample. Next, independence. Since we were given standard deviation in the problem, this one is already met as well. We were given the standard deviation of the population, which normally isn't known, but in this case it was. And then normality is just the fact that n is greater than or equal to 30, and we know this is true because our sample size was 500. So all of our conditions are met. Next, we're going to calculate our confidence interval. So say we want a 95% confidence interval. We would use this formula, and it would be 462 because that is the mean we found from our sample, plus or minus our z star for 95%, and this can be found on the chart that you were given, and this happens to be 1.96. I'm going to multiply it by 4.5 because, as we explained earlier, 100 over the square root of 500 is 4.5. So when you calculate this, 462 plus or minus that, you will get the interval, which is 453 to 471. So interpreting your results is saying we are 95% confident that the true population mean for SAT writing scores in high school seniors in Texas will lie within 453 and 471. Okay, so just to recap what we talked about, a confidence interval uses sample data to estimate an unknown population parameter with an indication of how accurate the estimate is and how confident we are that the result is correct. Any confidence interval has 2 parts. We have the estimate, which in this case is x bar, and the margin of error, which is shown by this formula. And the confidence level states the probability that the method we use will give us our correct answer. And we find this z star because it's standardized. Since our distribution we found is normal from our conditions, we can use the table to find our z star based off of how confident we choose the interval to be.